Lesson 46 is related rates problems. And we talk about related rates problems. We're talking about, we're relating multiple variables and multiple rates. And the rates are the parts that relate to our derivatives. So I'll take you through some steps here. It's kind of typical word problems in a way. You have to draw a picture, or I'm going to expect you to draw a picture. We're going to draw a picture, we're going to set up an equation, and work our way through it. Okay? So, example 1. A 13-meter long ladder leans against a vertical wall. The base of the ladder is pulled away from the wall at a rate of 1 meter per second. Find the rate at which the top of the ladder is falling when the base of the ladder is 5 meters away from the wall. Okay, guys. Picture here. We have what going on?
Sorry, straight wall like this. And I got another 13-meter long ladder leaning up against that vertical wall.
So what shape am I going to be forming?
A triangle.
Yeah, you guys see that right triangle happening? Okay, not sure that's the best, but okay, so you see my vertical wall, yes? You can just draw a flat-out right triangle if you want, but you see my vertical wall. Obviously, a wall makes a right angle with the ground, and then this slant is my ladder, and my ladder is 13 meters long, yes? Let's see, what else? A 13-meter long ladder leans against a vertical wall. I'm going to go ahead before I continue. I'm going to label my sides of my triangle X and Y just because I have to come up with variables to use. We can use X and Y, A and B, whatever. The base of the ladder is pulled away from the wall. So the base of the ladder is right here, yes? It's pulled away from the wall at a rate of 1 meter per second. And so what that's saying is that this side of the triangle is changing. X is going to be getting longer, yes? And so when we think rate, we're thinking derivatives. So since this side is X, my rate is going to be represented as the derivative of X. And so what I'm going to say as dx dt, because it's X is the distance, seconds is the time. And so what I'm going to include right here is that dx dt is 1 meter per second. So that right there, the fact that that side of the triangle is changing at 1 meter per second as the ladder is pulled out. Continuing to read, it also says, well, it then says, find the rate at which the top of the ladder is falling. So what does that mean we're trying to find this time? This side, okay? And so we're trying to find, as that ladder's going down, the change in this side. So the change in y is dy dt. And that's what we're trying to find. So that's our ultimate goal is dy dt. And we're finding the rate at which the top of the ladder is falling when the base of the ladder is 5 meters away from the wall. What is 5 going to end up going in for eventually? That's going to be your x value. So now we're not going to put it in yet, but we're going to think that eventually x is 5. So we're going to find dy dt when x equals 5. Okay, guys. It's a right triangle. We're talking about the 3 sides. What equation relates these sides? Pythagorean theorem? Okay, that's what you have to think of in every type related rates problem we do, is we need an equation that pulls everything together. In this case, it's Pythagorean theorem. What do you know about your Pythagorean theorem here? The ladder, right? So x squared, so the equation I'm going to write, which they call it the related equation in the book, is x squared plus y squared equals 13 squared. Okay? Now, in order to do this, we have to talk dx dt, dy dt, right? We're talking rates, so we have to differentiate. Meaning, we have to take the derivative. But since we have multiple variables, we'll use our differentials. Okay? Except it's differentials with respect to t, because everything's about time. T this time. Or time this time. Gosh, I'm tongue-tied, sorry. Derivative of x squared. 2x. And since that's an x term, I'm going to say times dx dt. A lot of times we just use dx in this case because it's in reference to time. I'm saying dx dt. Plus derivative of y squared. 2y dy dt equals derivative of 13 squared. 0, because 13 squared is a number, right? Derivative of a constant is 0. Now, depending on, I've seen this taught two different ways. We can do one of two things. You can either go ahead, and I think what I'll have you guys do, what are we trying to find? dy dt. So we can go ahead and solve this equation for dy dt, and then plug everything in, and hopefully we can come up with an answer. The other option is you could go ahead and plug stuff in and then solve for dy dt. It's just you don't plug stuff in until after you take the derivative, which we've done at this point. So let's go ahead and solve for dy dt. How do I get dy dt by itself? Okay, so first of all, subtract that term. So I'm going to leave 2y dy dt here. I'm going to subtract the 2x terms to the other side, so that's going to be a negative 2x dx dt. How do I get dy dt by itself? Divide by 2y. So then I'll have dy dt equals, now, what is negative 2x divided by 2y? Yeah, can my 2's cancel? Do you guys see that okay? That when I divide by 2y, my 2's are going to cancel. The negative will still be there. I'll have x on top, y on bottom. And then I'm going to put dx dt next to it. What? No. It'll all work out at the end. Okay, guys. We want to find dy dt. Do we know everything we need to know to plug in here? Maybe. We know x, yes? Talks about when x is 5, so this is the appropriate time to plug in 5. Do we know y? We're going to have to find y. Come back to that in a moment. Do we know dx dt? Yes, because that was when it was moving 1 meter a second. So, how can I find y? Pythagorean theorem, right? The ladder is always 13. At this particular moment, we're talking when x is 5. So the idea of using your equation, x squared plus y squared equals 13 squared. So 5 squared plus y squared equals 13 squared. So 13 squared, which is 169, minus 5 squared, which is 25. 169 minus 25 is 144. If y squared is 144, then y is 12. Now, do we have a y value? Okay, so you may have to find values at times. Okay, let's finish it up. In that, dy dt is equal to negative x, what am I using for x? 5 over y. What did we discover y is at that point? 12 times dx dt. What's dx dt?
1 meter per second.
That was labeled over on my triangle. It's off the screen now. So negative of 5 divided by 12 times 1. What is that? Negative 5/12, and fraction is fine. It's dy dt. It's change in y in comparison to time. So what's my labels? We're changing meters per second. So meters per second. Does it make sense that I came up with a negative rate of change? Why does it make sense I came up with a negative rate of change? Because we're talking about when the ladder's going down, yes? Okay, this one we were pulling the ladder out, and so that was a positive, but the ladder's going down here, so it was a negative. Questions? Okay, let's try and get one more done at least, or at least try and get it done. Really want to. Okay. A 6-foot tall man is walking straight away from a 15-foot high street light. At what rate is his shadow lengthening when he is 20 feet away from the street light? If he is walking away from the light at a rate of 4 feet per second. You guys remember these types of problems when we set them up for proportions? We're going to have a street light, you have the person walking, and the shadow, like the light shining that creates the shadow.
Earlier this year.
Well, essentially what we're creating here, okay, is similar triangles. And I'm cutting to the chase because of time. So this right here, this vertical line represents my light. And then I have to have a 6-foot human. There's my little human. Well, okay. So a 6-foot tall man, or as I said, human. There's my 6-foot tall man, and realize he's represented by just a straight line, right? I was trying to be, fancy, and he's a straight line. Okay, 6-foot tall man. He's walking away from a 15-foot high street light. So this side over here is 15 feet. And he's walking away, right? At what rate is his shadow lengthening when he is 20 feet away from the street light? So where is his shadow? If the light is here, it's shining on him. His shadow is down here. And actually, because I'm going to go with, I think it's what the book uses, I'm going to call this L. Just trying to be consistent with what the book uses here. But I'm going to call this L. And this is his shadow, in case there's any question. Shadow. Okay. Shadow. It wants to know at what rate is his shadow lengthening. So what are they asking me to find? If his shadow is L, at what rate is his shadow lengthening? That means I'm trying to find DL dt because his shadow is L. So we're trying to find that. And we're trying to find that. I'll put it up here actually. We're trying to find DL dt when what is happening? When he is 20 feet away from the street light, which, sorry, I didn't put a label over here. I'm just going to call this X over here. So between him and the street light is X. And so when he is 20 feet away from the street light, that's saying when X equals 20. Okay, guys. What else did I not use? I know I didn't use something. Okay, he's walking away from the light at a rate of 4 feet per second. So what's changing as he's walking away from the light? X is changing, right? The farther he walks from the light, the farther X goes. And so dx dt is going to be here, and dx dt is going to be our 4 feet per second. Now, okay, guys, do you remember similar triangles? Do you see a big and a small triangle there?
Yeah.
Oh, yeah. Okay. Okay, in my small triangle, the bottom is L, and the human is 6, right? Yeah. In my big triangle, my side is 15. What's the bottom of the big triangle? X plus L is what she meant, right? Now, similar triangles. Can you set up a proportion?
Yeah.
You have options.
I just don't remember what goes on top and what goes on bottom.
15 over 6, x plus L over L.
Yeah.
Or L over x plus L, 6 over 15.
Oh, you can do it either way.
Or 15 over x plus L, 6 over L. Or L over 6, x plus L over 15.
I just like the big triangle over the small triangle.
Okay. I mean, you know.
I didn't know you could do more than the one.
Oh,
I
yeah.
don't know what you're talking about.
Okay, so if we go, what do you guys want to go?
15 over 6.
Yeah, and then the x plus.
Okay, so if we go 15 over 6, 15 from the big triangle pairs with 6 from the small triangle. Just as, what else do we know? X plus L from the big triangle pairs with L from the bottom triangle. Cross products, and here, to address your question, Carly, I didn't know I could do it so many different ways. As long as your cross products match my cross products, any of those options work.
Wait, you can't just cancel out the L
Nope.
because it's adding out to another variable.
Yep.
So 15L equals 6x plus 6L.
Okay. 15L equals 6. Oh, gosh. X plus 6L. Put your L's together. Subtract 6L. Oh my gosh. 9L equals 6X. If you really want to reduce that another step, you could.
By 3.
Yeah, divide both sides by 3, and now I have.
3L equals 2x.
Okay. Now, I have yet to differentiate. I can't plug anything in till we differentiate. What's the derivative of 3L? 3, and then? No? dl dt. Because it's derivative of L. No, derivatives, not antiderivatives. What's the derivative of 2x? 2 dx dt. Okay. If you recall, we're trying to solve for dl dt. So you can divide the 3 to the other side. So then dl dt, 2 divided by 3 times dx dt. As it turns out, we're not even going to use x in this one. dl dt is 2 over 3 times, what was dx dt? That was the 4 over here. So 2/3 times 4 becomes 8/3, and that is feet per second. Thank you for bearing with me. I will make a recording of the last two so that you guys can go back and look at those at your leisure. Tomorrow is a work day. If you use some time at home tonight and your time in class tomorrow, ideally make it so you don't have homework over break, guys. That would be my recommendation. That was not my plan. I don't want you to have homework over break. Okay? So, exactly. So my thought is, listen to notes tonight, and then you can just get the homework done tomorrow, hopefully. And be good for the sub.
You know who's going to be?